yet, right? I need to activate it, no?
I can see some viewers.
I need to. Hello, everyone. So I think we are live, right? Can also someone check YouTube to make sure? Can you hear me?
Yes, we can hear you.
Can you check if the YouTube live stream is working correctly?
Yeah, it works.
Okay. So thanks everyone for joining. This is the first meeting for the a new PNS. It's the a PNS on hardware software co-design. And today we're gonna do the introduction. We're gonna introduce the course, and we're gonna also after that present the potential projects for the students. So my name is Konstantinos Kanellopoulos, and the course, of course, is under the supervision of Professor Mutlu, and it's conducted in Safari and Etihad Zurich. So first, the full title of the course is Intelligent Architectures via Hardware Software Co-Design. Is offered at this spring semester, and it's, I think, 3 credits. The language is English, of course, and the project will is around the multiple topics in the context of hardware software co-design. So, what is the role of this course? So in this course, we will introduce the need for hardware software co-design in current computing systems in order to achieve high performance and energy efficiency. And also the students, you will get familiar with the current as well as futuristic hardware software cooperative techniques. You will also learn how to modify software to match the underlying hardware and vice versa, how to modify, how to design hardware for the appropriate software. And you will also work hands-on with like analyzing workloads, creating new hardware software techniques, new interfaces, proposing new software and new architectural solutions. So what's the key takeaways of this course? So this PNS aims at improving your knowledge in computer architecture and hardware software co-design. So you will learn multiple concepts around microarchitecture, memories. It will enhance your technical skills in programming, both CPUs and GPUs, which depends on the projects you'll select. And you will also learn how to develop architectural simulators in some of the projects. It will also enhance your critical thinking and analysis. This will help you a lot in how you think towards research and how you can shape your vision and your thoughts. You will interact with a big group of researchers. Right now, we are 5-6 people here as mentors, but you can interact with more people from the group. And also you get familiar with key research directions that we pursue in Safari. And at the end, you will also perform a technical presentation of your project, which will help your presentation skills and how you communicate with the audience, right? So what is the key goal of this course? So the key goal is to learn how to design efficient hardware software cooperative techniques. And what are the prerequisites of the course? So first, it would be preferable and it would be help you a lot if you had taken in the past any like the digital design and computer architecture course or any equivalent course which is offered also this spring semester or in the previous semesters. You need to be familiar with C or C++ programming. This will help you a lot and give you a head start in some projects. Also, some familiarity with machine learning frameworks might be needed in some specific projects that interact with machine learning that have to do with machine learning techniques. And it's also crucial to have interest in the current computer architecture and the current computing paradigms and discover why things do or do not work and solving the problems the correct way. So our final goal is to make systems efficient and usable. So let's deep into who are we and more about the course info. So the course is offered by Professor Onur Mutlu, who is a full professor at the IEDM Zurich at the IT department, but he's also affiliated with the informatic department since September 2015. He is also holds a Stryker professorship in Carnegie Mellon University, and he received his PhD from UT Austin and worked at several industry companies. You can always reach him to his email, and you can check his website, the research direction, the different projects, how to apply to Safari, and different things. In terms of research and teaching, the group is interested in multiple different directions: computer architecture, memory systems, a huge focus on memory systems, hardware security, hardware software cooperation as this PNS, and as well as like architecture for bioinformatics, health and medicine. So let's take a look at the mentors. I am the lead mentor in this PNS, and I'm a PhD student in my second year. And I'm really interested in hardware-software interfaces, hardware-software co-design, as well as hardware security. And that's Rahul. Rahul, do you want to introduce yourself quickly?
Yeah, sure. I mean, yeah, so I'm also a PhD student in working with Professor Onur Mutlu, and I'm currently in my third year of my PhD. So yeah, so mostly my research interest lies in the intersection of machine learning and computer architecture. So specifically, how we can use machine learning to make the current architectures even more intelligent, more data driven. So yeah, in this course, I would we were actually thinking about some new ideas, new avenues, how to use some lightweight machine learning algorithms in current processes designs, and which would eventually help in tackling the problems that we are facing right now. So I'll go after this presentation is over, the initial introduction, to introduce you the project that we have in mind. Hope you like it.
Thanks, Rahul.
Thanks, Konstantinos.
Okay, so then Juan is a senior researcher and lecturer in Safari. I think he is not right now in the meeting. Then it's Hayu. Hayu, do you want to also introduce yourself?
Yes, I'm a postdoc researcher in the Safari group, and my research interests include the non-volatile memories, processing memory, memory security, machine learning, and the heterogeneous memory system and bioinformatics. Yeah, I'm happy to share my projects and to discuss with you. Thank you.
Thanks a lot. And Muhammad, who is also a postdoc at Safari. Muhammad, do you want to introduce yourself quickly? Muhammad? Okay, maybe he's not here. I will continue. Okay, and this is the whole Safari research group. And you can read the newsletter from 2020-21, where there are multiple information about the research, and the motto of the group is Think Big, Aim High. And this is, as you can see, the pre-COVID group. And right now we're more than 40 people. As I said, you can read the Safari newsletter from December 2021. It has multiple news regarding publications, regarding awards, infrastructure, interviews, and it's really helpful to get an overall understanding of what's happening in the group. We also have the live seminars. The live seminars are a series of talks from industry, as well as research talks, and it would be helpful to watch them because there are multiple discussions with industry. Like, for example, last week we had the last meeting was with the chief architect of Cerebras, a big machine learning accelerator company, and it was pretty interesting. So the current research focus areas of the group, as I said, it's mainly computer architecture, hardware, software cooperation, bioinformatics, with a really huge focus on memory and storage, as well as many other domains: energy efficiency, genome sequence analysis, system architecture interaction, GPUs. And you're gonna find out also from the projects in this course that we have a wide span and a broad research directions. So let's talk more about the course requirements and the expectations that we have. So first, attendance is required for all the meetings. You need to study the learning material before the meetings. Each student will carry out a hands-on project, which we'll discuss later. You will need to build, implement, code, and design with close engagement from the mentors and the supervisors. You need to participate and ask questions, contribute to thoughts and ideas during the meeting mainly, and read relevant papers. I mean the meeting with the mentors. And at the end, you need to perform a presentation, and you need to deliver a GitHub repository with the code that you developed. And of course, we will help the projects with good progress to get published in good venues if there is enough progress and the student is motivated enough. With respect to your responsibilities, we have one lecture every week. We will have probably 5 lectures. I'm not sure if there will be 5 consecutive ones. I think it will be 4 consecutive ones, and then there will be one on the 26th of April, but we're going to discuss that. The course takes place every Wednesday at 10:30 a.m. and it probably will last around 1.5 hours. The attendance is mandatory, but the most important thing is like working on your projects, which like really depends on the project and it depends on your expertise. But I would say it will take around 4-5 hours per week, but it really depends on you and your expertise at this part. And meeting your mentors weekly is required, which is much more important than attending the presentations, right? We're going to present research papers, but the most important thing is like meeting your mentors, because you can watch later the presentation of the papers if needed. So the course website is this one. You can find useful information for the course, and please check your email and Moodle frequently for announcements, as we will have also Moodle we will also use Moodle for Q&A and announcements. For example, until next week, we will use Moodle for deciding which projects you prefer and you would like to select and work on. Regarding the next meetings, we will give you a chance to select a project in the next meeting, and then we will have one-to-one meetings to match your interests, skills, and backgrounds with a suitable project. And it is important that you study the learning materials before our next meeting. And as I said, that we will assign the project next week. In the future meetings, we're going to present, we'll have a series of presentations of research papers, and we're also going to provide background tutorials on computer architecture topics, for example, virtual memory. And we're also going to provide tutorials for microarchitectural simulators, and we might also provide some tutorial on how to use tensor cores in GPUs, and we're working on that. And yes, so these are the technical parts of the logistics of the course. And if you have any questions, I'm happy to hear them. And if not, I will continue towards the topic of hardware software co-design. Any questions? Yes, all the slides will be uploaded. Yeah, everything will be uploaded, and you can also watch the live streams whenever you want.
I didn't quite understand. Are you presenting the different subjects next week, or are we supposed to next week find out what we're interested in?
No, we're gonna present them today after I give this intro, and then you have 1 week to select what you want. So we will have a poll in the Moodle so that you can pick your topic and your preferable topic.
Okay, cool.
Any other question? Okay. Let's first talk about the famous axiom that Professor Mutlu delivers in his lectures. So to achieve the highest energy efficiency and performance, we must take the expanded view of computer architecture. And as you can see here, we have the problems at the high level, then the algorithms, the system software, the interface between hardware and software, microarchitecture, logic, devices, and electrons. And during the previous years, mostly the architecture community was focusing on the system software and the microarchitecture and the hardware software interface. But right now we need to take a more expanded view and co-design across the hierarchy from algorithms to devices, and specialize as much as possible within the design goals to achieve the highest energy efficiency and performance. So in hardware software co-design, there are multiple ways to approach the problem and the topic. One way is to design application-specific standalone accelerators, and this can provide high performance and energy benefits, but lower flexibility. We cannot run any application in the standalone accelerator. We can run only a specific set of applications. One other way of approaching the topic is by extending general purpose processors with application or task primitive specific hardware components. This might also deliver high performance and energy benefits, but it requires abrupt changes in the processor. And the last is we need to also revisit sometimes the existing hardware software interfaces like the instruction set architecture to enhance performance, security, and portability. And right now I'm gonna dive deeper into some examples from industry and how things are shaping right now. As you can see, this is the Apple M1 Max processor. And as you can see, we have a neural engine inside right now in the processor. And the neural engine serves is like some type of systolic array that processes neural networks extremely fast. And this is embedded inside the processor, which means that we have a standalone accelerator inside the processor that is good only in one specific task. And this way, given the fact that we run too many workloads which use neural networks, we can benefit a lot in terms of performance and energy efficiency. Same case for encoding and decoding video. So there is a special encoder and decoder which handles videos inside the M1 Max processor. And this is one good example of hardware software co-design, as Apple is also designing both the software and the hardware in their system stack. Another good example is Tesla. Tesla released this Dojo chip and the whole system. The Dojo chip is a standalone chip that also performs inference and training. And as you can see here, the whole stack is designed by Tesla itself. So they designed both the software and the hardware to get the most out of the can from in terms of energy and performance. And I suggest that you take a look at this Safari Live seminar with the chief architect of Cerebras, who also talked about how they needed to go towards hardware software co-design, and they designed their own ML accelerator chip, which is really big. It has 400,000 cores, and it's the largest. It's I think one of the largest chips that exists right now in terms of ML acceleration. And they released also the second version of the engine with double the amount of cores, right? Which, as you can imagine, it's a really huge chip, and it requires lots of effort to design that, as well as the software stack above it. Google TensorFlow and TPU. Google introduced the TensorFlow and introduced also the hardware to run neural networks faster. The hardware is the tensor processing unit. So as you can see, in 2016, Google found out that and published a paper in ISCA 2017 where they found out that, okay, we have too many workloads which execute neural networks, and we find out that we cannot use the same processing unit for neural networks. And what should we use? And they come up with an old idea, which was a systolic data flow, a systolic array. We might talk later into the course about it. And they introduced a new chip so that they can run the neural network inference and training much faster and with higher energy benefits. And they released the second generation of the TPU, where they introduced also the concept of high bandwidth memory. They increased the bandwidth of the memory, and they also enabled training. And then they released multiple new versions every year to support more applications and increase the amount of computation that they can perform, etc., etc. So that's an example of a modern systolic array. So we have a matrix multiply unit, and the matrix multiply unit that serves as like the main component that performs the matrix multiplication extremely fast. And we also have some caches there some scratch pads and caches which are able to offer faster access to data. And all these are programmed and handled by the TensorFlow and the software stack that is able to use right now this matrix multiply unit. And that's the core concept of hardware software co-design. We designed TensorFlow to use the tensor processing unit, which we also designed. So how is the system architecture designed today? So it's human-driven, and humans design the policies, right? And how to do things. So we have many too simple and short-sighted policies all over the system. There is no automatic data-driven policy learning. almost no learning, and we cannot easily take lessons from the past actions. And the question that comes is like, can we design fundamentally intelligent architectures? So one intelligent architecture needs to be first data-driven, and the machine, the processor needs to learn the best policies and how to do things. It needs to be sophisticated, workload-driven, and changing with far-sighted policies. We need to understand what's going on based on the workloads, based on the data. And we need to be automatic and data-driven policies. We need to have automatic data-driven policies. And all controllers right now that exist in the system are intelligent data-driven agents, and we should design them this way. And the question is, how do we start? So there is this work from 2008 from Engini Peck, and Onur, Professor Mutlu is also a co-author. It's called the Self-Optimizing Memory Controller, a reinforcement learning approach, where they demonstrated that using reinforcement learning in the memory controllers can lead to state-of-the-art performance. And they use it to create a memory controller that is data-driven and learns from data rather than having a static heuristic-based policy. PTI is also a recent work that Rahul published in Micro 2021, where we demonstrate that we can also employ the same technique for prefetching. We formulate the problem of prefetching and fetching data proactively from memory into the cache hierarchy. And the prefetching decisions are made using Pythia, using a framework that's based on reinforcement learning that learns based on the data. I suggest you will read these papers as they're in the required learning material. So we want data-aware architecture. So data-aware architecture understands what it can do with and to each piece of data. And it makes sense to use different properties of data to improve the performance, efficiency, and many other metrics. Some of them are like, how compressible are data? How approximable are data? What is the locality of the application? What is the sparsity? What are the access semantic? What's the memory access pattern? So one problem is that right now, modern systems have limited expressiveness, and the high-level information are not visible to hardware. So in software, you use data structures, optimizations, access patterns, different data types, but the hardware at the end of the day, it sees ones and zeros. It sees ones and zeros, which it's trying to decode as instructions and memory addresses. And what is the solution? The solution is a more expressive interface. So we introduced in 2018 a new expressive interface called XMEM, which is communicating. It acts like a bridge. It communicates the higher level program semantics to hardware. And this way we enable powerful optimizations. You can take a look at the paper. It's called The Case for Richer Cross-Layer Abstractions, Bridging the Semantic Gap with Expressive Memory, published by Nandita Vijay Kumar, who was my mentor, by the way. And it was published in ISCA 2019. And the same expressive interface, it's another paper, the locality descriptor, which also communicates higher level semantic information about locality to increase performance in today's GPUs. Another example of hardware-software co-design is IEDM, which was used for deep neural networks. So deep neural network evaluation is very DRAM intensive, especially for large networks. And some data in layers in deep neural networks are very tolerant to errors. So what we want to do is reduce the DRAM latency and voltage on such data in layers. And we want to do that while still achieving a user-specified DNN accuracy target by making training DRAM error aware. So we want to train the network in a DRAM error aware way so that we can incorporate the errors into our model and do not sacrifice accuracy for performance. So at the end of the day, we want to perform data aware management of DRAM latency and voltage for deep neural network inference. I'm giving you an example here. So we use a DRAM chip, which is partitioned into 4 voltage domain that can use many to 4 DNN to DRAM mapping. So we use 4 different voltage values with error rates indicated by the yellow, red, and green lines. And what we do is we map the more error tolerant DNN layers to DRAM partitions with lower voltage and latency. And this way we benefit in terms of performance and energy. These are the 4 different layers, right? So you can take a look at this paper also. It was published in Micro 2019, and this will be also in your required readings. Another relevant method of hardware software co-design is another work we published in Micro 2019, where we actually co-designed the compression algorithm for sparse matrices, and we introduced a new hardware module enabled to accelerate how you index and find the non-zero elements in a sparse matrix. There will be a presentation on this paper next week. Another data-aware virtual memory framework is the virtual block interface, which was introduced by Nasser and Hadzinazar in ISCA 2020. And here we introduced an alternative way of designing virtual memory to incorporate metadata, delegate the memory management to hardware, and be more data aware and lead to higher performance and lower address translation overheads. So, that's where my presentation ends. And I hope I gave you a good introduction into the topic and how research and industry, academia and industry are shaping towards the topic. And I think I will stop